All right, it's about that time we can get started. So, welcome to Organic Chemistry 2. My name is Ryan Morelli. Call me Professor Morelli, Dr. Morelli. When you graduate, you can call me Ryan. I think we'll start today. I just want to sort of introduce you guys to some of the resources that we have available for you, go through the syllabus, and then we'll get going into some of the chemistry. So obviously you guys have all been through Organic 1, so there's a certain expectation of knowledge base that you have, and so we'll discuss that a little bit so that hopefully you can all be successful in this class. All right, so in terms of resources that we have, I think I keep my own website with all the course material. I don't use Blackboard that much except when I'm posting your exam or quiz grades for you guys to see. That's the only time when you would actually probably need to use Blackboard, unless I occasionally will send out messages through there. But if it's something critical, I would probably also post it on my website, as long as I can get access to my website. So the thing about my website is that I can really only make changes on campus. So if it's a situation like the blizzard, I could probably do stuff on Blackboard, but I wouldn't be able to do stuff from home on my website. Now to get there, it turns out there's not too many Morellis, so you can either find it through you can either find my website through Brooklyn College's homepage, or you can just put my last name into Google. There's not many of us, so it's the first thing that shows up. That's convenient for you guys. And my website, again, you can sort of go right to what you need here, but I'll just go to the sort of first page. You can see over here on the left is most of the information that you would need, and specifically sort of course information for chemistry that you'll find over here. Note that I'll have materials for Organic 1 as well. There's been one change to this year's Organic Chemistry 2 class that was kind of a new thing, and that's that carbonyl chemistry was not covered last semester. It's historically been covered in Organic Chemistry 1. Given some of the changes that happened in terms of extra time for Organic 2, we decided to take Carbonyl chapter out of Organic Chemistry 1. I didn't teach Carbonyl chemistry last semester, so there will be no material in terms of under the Organic Chemistry 2 site, but there will be under Organic Chemistry 1 because when I taught Organic Chemistry 1, I had some of this material. So again, you can find all my old material. In particular, what could be valuable for you is even some of my old playlists, so you may actually want to look back for this. Again, I'll post my videos online for this one, but if you look through, I forget exactly where it is, but I think it's the 1010, but you can search through. There's like, I think, 3 classes that have carbonyl chemistry on them if you want that. So if you want to get ahead and you don't feel like reading the book, you can sort of watch some of my old lecture videos. And then again, you might find some questions in terms of old stuff. Again, because in part this is a course that is additive, and so it's going to be expected that you have a certain level of mastery of Organic Chemistry 1. So there's that material there if you need some additional stuff to take a look at. Now, in terms of Organic Chemistry 2, I do have some of my old quizzes up here. I still have to update some of the keys, as well as I can't find the electronic copy of Exam 2, so I may need to scan that one in. But I'll try to have that one up for you guys as well. That's an advantage, I guess, that you guys will have over the people last semester because I didn't have this information. Now I'm going to be posting the lecture videos shortly after class, so you'll be able to rewatch them. But if you want to get ahead, in fact, it may even be better than reading the book, perhaps, to actually go and look at some of my old courses and just watch the videos of my course from last semester. Again, because this is the stuff that was obviously in my classes, the stuff that I find most important, so it's going to be fairly valuable for you guys if you want to kind of get ahead. And again, the book, I got to be honest, I don't use the book too much, so this could be a little bit more valuable for you there. All right. Still a bit. There's also some handouts here that you'll see down here that you can sort of read. A little bit of additional reading, specifically later on in the semester when we get into things like Biomolecules. I wasn't a big fan of the book's discussion on these. Well, I shouldn't say that, but I thought there was some additional material that I thought would be better. And so, again, you can sort of take a look at my old videos from that standpoint to see what I specifically find valuable. All right, the syllabus. First of all, I already sort of introduced myself. If you need to contact me at any point, you can certainly try calling me. I actually don't know how to check my voice messages. I've been here for 40 years. I can only imagine what's on there at this point. So you can certainly call me, but if you leave a message, as I just sort of told you, it won't get answered. So if you call me and you don't get through to me, shoot me an email. And again, I'm usually pretty good at getting back fairly quickly. But again, sometimes I'm either getting bombarded by emails or I have something else going on. But I'll try to get back to you in a fairly quick manner. If you've emailed me and a couple days goes by and you still haven't gotten a response, just email me again because I probably just overlooked the email. So my office hours, they're going to be effectively right after class from 11 to 1. My policy with office hours beyond this is that you can certainly make appointments with me. It can often be difficult for me to sort of make additional appointments. Oftentimes what I'll suggest to students is just try popping by my office. And if I'm in there and you have a few questions, I'll usually make myself available to you unless I've got something really busy. I kind of think what I usually say is, my door's open, feel free to come in, see if I have questions, but I sort of reserve the right to throw you out. But usually, you know, unless there's something really pressing, I'll usually make at least a little bit of time for you. So certainly don't hesitate to stop by my office and sort of ask me questions. Great question. I didn't even post here. 437 New Ingersoll. Wow, that's a complete. The fourth floor, right by the middle elevator. 437. Wow. Yeah, I guess that would be important. Again, here's the textbook material. You know, again, I'm a big proponent. You know, I think that. I think the thing that's going to, hopefully at this point, you guys have passed Organic 1, so you're able to at least communicate organic chemistry, you're able to draw molecules without making tons of mistakes, you're able to draw mechanisms. And I think my advice to you guys in terms of the textbook would be certainly use it as a resource. What I've always sort of told people is, I think organic chemistry, we don't really, it's very difficult to talk organic chemistry, I think. Even if I'm having conversations with some of my friends who are organic chemists, sometimes it's difficult to sort of have a discussion without actual structures. And so oftentimes the sort of advice that I'll give to students when they're reading a textbook is to try to understand the figures, right? So sort of look for the figures, try to understand those figures, and then subsequently use the text to try to help you understand the figures a little bit better. That'll work for a lot of people. It might not work for everybody. Some others will really actually need to read the textbook from front to back. But again, there's something that you can certainly try. But what I would say is that the most important thing is going to be that you pay attention in class because, again, this is my class. I'm going to sort of emphasize the things that I think are most important. Those are going to come up in the class. I would also say I had a situation last semester where I forget what happened, but I said something, and I wrote something on the board that, without what I had said, implied something completely different. And students came to me and said, "Oh, but look, I wrote this down in my notes." And I said, "Yeah, but this is what I was talking about." And they completely sort of misunderstood what I said. If I were you guys, I would leave your notebook home and just focus on the class. I have my video lectures, so really focus on what I'm trying to say. Ask questions if you're not understanding anything in class. Because again, the videos are there if you need to go back and look over them. So you can sort of look at them, you can take notes, but I think it's really important that you guys pay attention to what I'm saying and not simply try to scribble down everything that I read on the board. Okay? So again, that's going to be the best thing. And then, as you've seen time and time again, it's also important that you problem solve. And so, again, there's a lot of problems that are up there. I think the types of problems that Professor Horowitz puts up are fantastic. So if she's got questions on her website, those will be good. I think there's questions from old Jim Howell exams, for example, that are particularly challenging, that I think represent really good practice problems to sort of prepare you guys. And then I'll have materials that will be available to you guys as well. As some of you know, some of you may have heard, I'm very, what I view from this course, my objective that I'm looking to try to teach you guys is not to teach you guys a whole bunch of organic chemistry. That's really not my role here. My role is to really make you guys able to communicate organic chemistry, be able to understand things, and be able to problem solve. And so one of the things that you will see is there'll be a very heavy emphasis on mechanisms. So any reaction that you've done, you should understand that mechanism. Chemistry takes place through mechanisms. Understanding mechanisms of different reactions will allow you to see a new reaction that you've never seen before and actually be able to predict what that reaction is. In addition, I'm a synthetic organic chemist, so I'm big on multi-step syntheses. That's another big thing that you guys should really work on. Again, I sort of view organic chemistry as a real good opportunity to push yourselves within the context of problem solving, because I know that very few of you will actually end up being organic chemists. If any of you, maybe there's a handful of you that might actually end up being organic chemists, but certainly all of you will need to be able to problem solve in whatever career you have. And so I think that's something that we really try to push here, get you guys good at problem solving, and so forth. All right, in terms of the course evaluation, there is a recitation attendance. Again, that's just to sort of motivate you guys to show up through recitations. Really try to be active in those recitations. I know sometimes that's difficult at 8 o'clock in the morning, but I think that recitations can oftentimes be one of the most valuable things that you have. And so if you sort of make the most out of it, if you really are active at participating, that's one of the areas that you'll get lots of feedback. And I think that's important, right? I think that one of the biggest issues that I've often seen with students is that they will do a problem and they get it wrong and they might not completely understand why it's wrong, or they might get a problem that's like somewhat right, or they think that it's right when it's actually not right. So one of the ways you get feedback is certainly in working with some of your peers and coming to office hours, coming to your recitation instructor's office hours, and again, being very proactive in recitations. Don't feel bad in a recitation. In fact, your instructors will probably like it if you come into the class and you say, can you really go over this one question in class? I think that they will sort of appreciate that. So again, recitations is 5%. Your quizzes, I always feel like I have to have this right up front because it's actually gotten much better now that I'm sort of up front with it. Your quiz grade is going to be based upon your top 4 grades. This isn't because I think that you're going to have a bad day on one of your quizzes and you're not going to do well on the quiz and so you can drop your lowest quiz. That's not why I do it. The reason I do it is because we're a commuter campus. And by and large, probably over half of you are going to miss a quiz. And I don't want to overpenalize people and give them a 0. That's why I drop the quiz. If you happen to be missing a quiz, then it's just going to end up being a 0. Now, if you let me know in advance, right, then I have no problem with taking somebody and moving them over to a different recitation section to take a quiz. The problem is that there's a whole bunch of people that might be taking a quiz on Friday, and if they miss it for whatever reason, when am I possibly going to have them make it up, right? And so if you're a person that's on Monday and you're like, oh, but there's so many other recitations that I can go to, it's like, yeah, I get that that would work for you, but it doesn't work for me trying to run this class, because it's not fair to the people that might be on the last quiz day, because when are they going to make it up, right? So the policy is, if you know you're going to miss a quiz in advance for basically whatever reason possible, except for I need more time to study, right? If it's a family, if there's a holiday and you're not going to be able to come in that day, if there's a wedding, if something happens in advance, or even if you think something might happen in advance, work with us. We'll get you into a different recitation section. But again, you need to let us know in advance because, as you guys might have seen, the recitations are getting pretty flooded, right? There's been a lot of people in the recitations, and if it's a situation where specific person might not be able to accommodate you, then there's nothing that we're going to be able to do. So I would highly recommend that you let us know in advance. And again, if you let us know in advance within 48 hours, then we should be able to accommodate you. If you let us know the day before, we might not be able to accommodate you. And so if I say, sorry, too late, then that's the case. So let us know 48 hours in advance. But again, even then, the sooner the better, because then we can sort of accommodate you better. All right, lecture exams. And again, that quiz, that dropped quiz, like, I always feel like I have to say this. Like, it literally means, like, if you miss it for whatever reason, like, you can certainly let me know. And if you miss 2 for, like, legitimate reasons, if you've just been having a bad semester, like, I don't want to overpenalize you, so I'll allow you to, I'll allow a makeup if, say, for example, you miss 2 for legit reasons. But again, that one could really, like, I've had situations where people have gotten in car accidents, right? And I've been like, sorry, like, I'm sort of almost in this draconian position simply because it becomes a very slippery slope. And again, that's the reason why I dropped it. Lecture exams. You'll have 2 of them. The first one, again, will be March 9th. I've already gotten an email from a group of people that have some other campus-related thing where they're actually going to be out of the country. Again, if you miss the lecture exam, there will be no makeups. It's too difficult for me to make up the makeups. Sorry, to write makeup exams. If you miss it for a legitimate reason, you know, or even if you miss it because that's the day you get to, you know, you total your car or something on the way in, I will basically make your grade based upon the remaining grades. You won't be getting a 0 for the lecture exam. But it has to be some type of excuse. You can't say, oh, I decided not to take the second exam because I did so well on the first exam, and I, you know, I mean, I don't risk that. I have a legitimate excuse, and that's fine. And then again, the final exam will be the big one. I think the date might be posted now, but just check it. When I tried to post it, just sort of. Here we go. I think it's posted. I think I saw it. It was shortly after I did it. Just go to this website. I think it's the first day. We're usually the very first day, because I think it's the Monday. We're usually, I think, the first day. But if you just go here, that'll tell you when the final exam is. We're just going to go based upon when the final exam schedule is. And we are Monday, Wednesday at 9. So NW9 will be the sort of code that is us. So in terms of everything else, if you end up missing the final, again, we have a specific day the following semester. Hopefully try your best not to miss the final. But if something happens, again, this last semester I had a student who actually did get in a car accident the day of the final. And he showed up and it was like 20 minutes left. I was like, dude, just take the exam next semester. Like, you know, you'll get the incomplete. We'll give it to you next semester. This is organic chemistry 2, so it's not like, you know, it's organic chemistry 1 where you need to take organic chemistry 2 next the following semester. Like, we can work around that. But again, try not to miss it. Homework, do everything you can find. Again, I have the stuff that's available. Again, as I sort of said, it's about problem solving. So the more problems you do, the better off you're going to be. I don't generally like doing problem sets because what I find is that people will do a whole bunch of problems and then they'll just stop. And what I found, especially during, I think, my first semester here, and I sort of threw a little thing at people, was that they would just do the ones that were there, and then they would feel fine. It's like, no, keep working until you feel confident, which will probably be never, right? You just keep working, and hopefully the exam comes and you do well. And what I did actually one semester was there was a question in the book that came right after another question that was very similar, and I didn't assign that, and then I put it in the exam to see who would actually know it, and very few people got it, and I was like, okay, well, you know, just keep doing questions. Important dates, whatever, you guys can read those. But sort of that's that. Again, just pay attention to when important things are. Again, the quizzes will be held at your recitation sections. Again, I sort of just said that if you're going to end up missing it for some reason. The one funky one was like, there's one quiz that's like the Monday section, but it's actually on a Wednesday. So it's on the 18th, it's a conversion day. That was the only sort of potentially confusing thing. Besides that, I tried to be as clear as possible. Okay. All right. One other thing before I get started talking about chemistry, or actually going through the material, Periodically throughout the semester, we will have seminars upstairs in 432. So you'll hear me advertising for different speakers that I happen to have coming out. Generally, they're sort of organic chemists. We actually do have a collaborator that's coming this semester, and so I have the opportunity to actually advertise the first speaker, which is actually me. So I've got my 10-year tour coming up this upcoming fall, and so I had Brian Gibney put me on the seminar schedule. It's going to be in 2 days, so it's going to be Friday, 4:32. I just posted a whole bunch of flyers around. I am known to give questions that might come up at these seminars, so you know, it would certainly be something that you should be able to figure out otherwise. But the talk will effectively be on the research that we do here. It's a lot of synthetic chemistry, and specifically how a lot of the methods that we've developed can actually be used in a variety of different drug development pursuits. So we've got some pretty cool stuff going on for bacterial resistance, hepatitis B, HIV, herpes simplex virus. It's a recent thing that we've got going on, cancer. So it's kind of cool. I think a lot of you guys probably have interest in medicine, and so it would be an opportunity for you guys to get to hear about some of the research that the students in my lab are doing, and how you can sort of develop chemistry with an eye on it really being a powerful tool for drug development. And so that's 432 New Ingersoll. There's stuff posted on your way out. So yeah.
All the lectures on Friday?
Yes, and there's the one that's not going to be on Friday is the Frieden lecture. So that's going to be May 14th, I think, and that's one that I highly, highly, highly advise that you guys go to. Every spring we have, it's our sort of flag, I guess it's our big annual lecture, and that's always held on Thursdays. And so this year's Friedman lecturer is a person by the name Tom Muir, who's sort of a chemical biologist. He's somebody I really wanted to come. I'm actually chairing the Friedman lecture. I've done it for the last few years. And we'll talk a little bit about stuff related to what he does in advance of the Friedman lecture, but that's the only one that will be held on a Thursday. They're generally on Fridays. Periodically, somebody might have somebody coming out that they can't get in on a Friday, in which case it would be like a special seminar, but generally Fridays. So, okay? All right, any questions? Okay, so the beginning part of this course, I've actually, as I was looking at carbonyls and starting to think about the first few lectures, there's a really nice blend that kind of in retrospect doesn't really make sense. Well, I guess whatever, it all makes sense because it all blends together, but specifically carbonyls, I think really is an excellent starting point for organic chemistry too. And so it actually ends up working out really well because you'll see a lot of the chemistry, probably the first month or so of chemistry really evolves around chemistry of carbonyls. So what's a carbonyl? So a carbonyl is effectively any molecule that has a carbon double bonded to an oxygen. And I think there's a lot of parallels that we can draw between things such as carbonyls and alkenes. And so one of the things that I would sort of really urge you all to do is that when you're learning new reactions, if this hasn't been a strategy you've taken in the past, anytime you're learning a reaction, I think it's always best for you to try to compare that reaction to chemistry that you've seen before, right? And that way what you end up doing is you solidify what you had previously learned and effectively building upon the base of knowledge rather than trying to make them all seem like new things. And so as we begin to start to talk about carbonyl chemistry, I think it's probably valuable for you to start thinking about how there's a lot of comparables between alkenes, which is probably one of the last things that you guys learned, maybe before, maybe NMR, and sort of carbonyls. And so when we started talking about alkenes, right, one of the things that we learned, and perhaps a classic reaction that you initially learned along the lines of alkenes, right, is that if you take an alkene, you treat it with acid and say, for example, water, and we begin to think about the mechanism of which this will add water across the alkene. First thing that you're going to want to do, right, is sort of figure out what the most reactive component is in the reaction, and then start to think about what would be available to react with. And certainly water can be protonated as H3O+, so certainly that can go in that direction, but the alkene is the sort of reagent here that we care most about, and so the productive pathway is going to come first and foremost through the reaction with this alkene. And so perhaps this is one of the very first reactions you guys learned last semester. The reaction is going to evolve. The very first step is being protonation of this alkene, right? And as you guys should all know very well, right, there is going to be protonation, and the proton is going to end up on the less substituted carbon. For what reason? Stabilization of the cation, right? So if we protonate on the other side, then your carbocation, we have a less substituted alkene. There's this factor that's involved, right? Hyperconjugation, again, where you have all these protons that are hanging around here, and right, and all these electrons that are sitting around there are effectively being plugged in a little bit to that carbocation, helping stabilize it a little bit, right? And so this sort of factor of hyperconjugation will stabilize that. This is the sort of the base of why a more substituted carbocation is going to be more stable. Right, and then the second step in this reaction, right, will be sort of the water, right, has a couple sets of lone pairs on them. One of those lone pairs is going to subsequently go and make a bond with this carbocation. We're going to be shifting, right? The charge, in essence, is going to go from being on this carbon now to being over on this oxygen. Right, conservation of charge, conservation of mass, right? We have the same amount of atoms over here, the same net charge over here, or sorry, the same charge here is the same charge over here. And then again, what's going to happen at some point is that water, or we're going to regenerate the H plus in a way, so we can think about something like a base or something, plucking that off. Right, so usually there's some type of conjugate acid. I just started with H+, so effectively we're just going to have that fall off. Again, it's probably going to be plucked off under the media by water or something else. But that's the net process, right, is that you're going to get the addition of water sort of across this double bond. And so as we start to think about carbonyl chemistry, I think it's often best to sort of introduce it in a similar way to say, what have we seen previously? What's the reaction we've seen previously with alkenes, and how can we perhaps translate that to carbonyls? Now, in the case of a carbonyl, right, I've just sort of drawn acetone here. We have, and we say, for example, run the same reaction. Now, it turns out this is just not, this is going to be a fairly reversible process, okay? But if we start to look at similarities in terms of the chemistry that's taking place here, and we were to take a look at that carbonyl and have it react with acid, right, what would be the first thing that you might think would happen? We're going to protonate. And if we're going to protonate this molecule here, right, where's the proton going to end up? Is it going to end up on the oxygen, or is it going to end up on the carbon? Right. Okay, so some of you right now are saying, well, why would I know that? If we think back here, I think I had a few lectures on carbonyls that you can sort of read about. But if you start to think about the sort of charges and the sort of resonance forms, in many ways what you can sort of end up thinking about the reactivity of an alkene, right, is that the more substituted carbon, right, is going to be the one that's going to end up bearing that positive charge, or a delta positive, and you could imagine putting a negative charge over here. Now, certainly this is going to be the major resonance form, but at least in terms of reactivity, in a lot of ways, it's this resonance form that has illustrated this first reaction, right? If we try to do it the reverse, right, then the positive charge would be on the carbon, negative charge would be on the other side, and that's not going to work out that well. And so oftentimes what we can do is think about a delta plus, a delta minus, just to sort of think about the partial charges that are of those different things. And so a similar thing can happen here, right? We can imagine two different resonance forms, right? One where we have a positive charge on the carbon, one where we can have a negative charge, right, on the carbon, and a positive charge on the oxygen. And one of the things you may sort of ask yourself right away is, well, which one of these might be more significant, right? Which one would be a better contributor, if you will, to the sort of resonance hybrid? And again, as many of you sort of might have expected, based upon saying that you were going to protonate the oxygen, perhaps without even realizing it through this method, is that it's, in fact, this one is not going to happen. You're more likely going to want to have this resonance form, right? And why is that? Right, so your oxygen is more electronegative, right? And so, in fact, when you look at a molecule such as this one here, it's going to be this resonance form that's going to actually be related to the reactivity of this compound. We're going to see similar types of resonance explaining relative regioselectivity a lot more down the road, especially when we talk about aromatic compounds. But for now, we can sort of see this as the major one, and for those reasons, right, the more nucleophilic site, right, is going to be that oxygen, right? And if we think about this chemistry taking place, what's going to happen, right, is that we are going to protonate, right, that oxygen, right? The net result is going to be that now we're going to have a positive charge on this carbon, right? And then water can add in. Now, it turns out, as we'll sort of discuss in a moment, all these reactions are reversible. And again, once that falls off, what we're left with. Okay, so what we're left with here is a species known as a hydrate. Okay, this is a hydrate. Okay, hydrates are highly unstable. Why am I showing this reaction? Simply to its initial, at least, make the comparison and recognize that similar chemistry can happen with alkenes as with carbonyls. I thought it was a good sort of first sort of illustration of chemistry on carbonyls. But it's sort of important to recognize that this whole process, this is something that's going to be important as we sort of move forward, is every process in here is reversible, right? And so this leads to a proton, right? If we want to go in the reverse direction, simply these lone pairs will make a bond here. If we start thinking about the reverse direction, those protons are going to grab that one, right? Then what's going to happen here is this bond is going to leave, right? That's going to go in the reverse direction, right? And then what's going to happen here is, I guess, something's going to pluck that off, and you're going to sort of generate the polar product. Okay, so again, this is simply to show the analogy between alkenes and sort of carbonyls. As it turns out, this process is very difficult to make hydrates. There's very few instances where you'll actually be able to see hydrates, because it turns out that carbonyls are thermodynamically, in general, a very stable molecule. And so this is at equilibrium. It's going to mostly favor this direction. There are a few exceptions, specifically instances where you destabilize the carbonyl. So one example of a reaction that would actually go in the forward direction is chloral. This is chloral, okay? As you notice, there's a lot of chlorines on this carbon. What do you know about chlorines? They're electron withdrawing, right? And so through an inductive effect, you are destabilizing this carbocation in that position. So this is just one of the rare examples where if you take this and you treat it with, say, a little bit of acid and water, you're actually going to get one of the few examples where you actually get the hydrate as the major product. This is chloral hydrate. I think it's actually like a knockout drug. But anyway, this is one of the few examples where you can actually make the hydrate. More generally, we may see the reverse sort of direction. All right, now while this is reversible, the reason why this is reversible is in part because this is so much more stable, okay? There will be instances, and so if we take this to the next level, And instead of making a hydrate, there are molecules and there are reactions that can take place with very similar mechanisms that are productive. So to date, we really haven't seen, at this point in the lecture, we really haven't seen a productive reaction because this isn't really something that you would, for example, use in a synthesis, simply to illustrate the mechanistic similarities. However, if you take a carbonyl, and instead of treating it with acid and, say, water, let's say you treat it with acid and, say, methanol, and for the sake of actually having something, SO3H, we'll make a sulfuric acid, so it's a little bit less, theoretical. What can happen here is that this is a case where you can have a productive reaction. Okay, and in this case, what you end up getting is what we call a ketal. Okay. Now, sometimes you'll hear it called ketals. Sometimes you'll hear it called acetals. The key in the ketal is simply I didn't discuss the nomenclature yet. Okay. This is a ketone. I'll get to the nomenclature after I go through this mechanism. I should have discussed nomenclature first. But we'll discuss the different types of carbonyls in a moment. But the ketone, the key in ketal comes from the fact that this is a ketone. I'll get to the nomenclature as soon as I go through this mechanism. Okay. All right. So again, the mechanism is going to be very analogous to what we see over here. We are going to protonate and what we're going to have is methanol. Now again, this is a reversible process, as we said previously. And something slightly different is going to happen here. That in principle can happen in the other reaction that we saw over here, and certainly would be an intermediate. But what I'm going to do is I'm actually going to show how we've got a little bit of desymmetry here that we didn't have here. In this case, we have OH, we have OH over here. In this case, we've sort of desymmetrized this ketal a little bit because on the one hand we have methoxy, and the other hand we have this hydroxy. Okay, and so what's going to happen here, again, it's probably not going to be intramolecularly driven. Maybe something will protonate it and so forth. But the important point is that we're going to generate water as a leaving group. And this is what's going to be very important about the relative reversibility of this process. Okay? In other cases, no matter which one we formed, we're going to have water. In this case, what's going to happen is we're going to have water be the sort of leaving group. Okay? And at this point, again, there's different resonance forms you can draw here. So some people might say, well, right? And again, there's a carbocation. You can imagine a resonance form where the lone pairs on the OMe are actually making carbon-oxygen double bond. I'm just going to show it as this form because I think perhaps it's a little bit easier to see. Right? And now if we're in the solution of methanol and we have this carbocation here, what's going to happen? The methanol can now add in to where this carbocation is, right? And so methanol is going to add in. Right? Conservation of charge. Now we have that positive charge on the oxygen there. And then again, in this case, I've actually shown it with OSO3H minus. So this is our conjugate base. That's going to pluck this off. What we're going to get to there is the product. Okay? So in this case, you actually can do a productive reaction. There's an important difference in these two. And that's the fact that what we're doing here is we're doing this reaction in the presence of methanol. Okay? And at a certain point, what happens is we lose water. Okay? Now, this is where some of the trickery that a synthetic chemist can play is sort of at stake here. All of these reactions are, in essence, reversible. What can often happen is when you get to that step where the water is lost, right, there are things that we can do to actually get rid of the water. There are things called a Dean-Stark apparatus, which is effectively you boil off the water and replace it with fresh methanol. There are things called molecular sieves, which effectively will absorb water, taking them out of solution, right? But what happens here is on this step right here, we effectively render it irreversible by pulling the water out of solution. Okay? By pulling out of solution via Le Chatelier's principle, right, we're going to drive the equilibrium all the way here. Thus, the only product that we're going to see is this one over here. Okay? This is the first reaction that I'm showing you guys with carbonyls. Now, with that in mind, right, we've done this reaction where we've effectively pushed the reaction in one direction based upon taking water out of the reaction. You should be able to actually predict another reaction that could form. Reverse reaction. If we started with this compound, and let's say we wanted to go back to the carbonyl, what do? We add water. Thus, in about 2 seconds, 10 seconds, I just taught you a second reaction. And that's this one right here. Add water, we can go in reverse direction. So given time, I'm not going to go through that reverse mechanism. I would urge you all to try that on your own. Think about how this, in the presence of acid and water, will actually go back to the carbonyl. Okay? All right, so why is this sort of important? Well, again, we're sort of building here, right? We know this reaction with alkenes. Well, here's a hydrate equivalent. Okay, well, the hydrates are kind of a neat little, all right, whatever, but perhaps not practical. But here's an instance where there's a reaction that's very, very practical and very, very valuable. And it's valuable for a few reasons. And certainly ketals and acetals are found quite a lot in sort of valuable compounds. Just off the top of my head, artesunate, for example, is an antimalarial compound that has a, I think it's artesunate that has a ketal in it. Could be making that up. It's got very ketal-looking like things in it. But anyway, again, it's certainly a valuable structural moiety. But even more than that, this is oftentimes, as we're going to see, carbonyls are very valuable synthons. When I say synthon, I mean something you can actually use as a synthetic tool to actually construct bigger molecules. In the same way that, say, for example, alcohols were really good synthons. Right? So we'll talk a little bit about carbonyls and all the different chemistry that we can do with them. We're going to spend a good couple days talking about this. And you're going to notice that there's a lot of parallels between how versatile a carbonyl can be and how versatile alcohols can be. But because of that same versatility, right, that we saw, say, for example, with alcohols, there's always something that we would often have to do with alcohols when we wanted to use them in synthetic sequence. And that was to protect them. Right? So you guys learned about silyl protecting groups, right? You put on that silyl group under certain conditions, you take it off under different conditions. Ketal protecting will be the analogy that we have with carbonyls. So if you're doing a synthesis and you're nervous that you have this carbonyl that might undergo chemistry that you don't want it to do, you can always protect it as the ketal, right? And then when you're ready to go back in the reverse direction, you simply treat it with acid and water. Okay. Now I'm going to admit, I just haven't looked at my notes yet, so I don't even know. All right, so now, so this is where we are. Okay, so again, I was trying to make sure that we could sort of compare alkenes to carbonyls. And so what I'm going to do with the remainder of this class today is we're going to talk a little bit more about chemistry with carbonyls. I'll come back to condensation chemistry, perhaps a little, maybe in a couple classes. I thought it was a really good one for mechanistic studies. I think it's a good one to sort of mechanistic practice. I wanted to sort of put that up there. I wanted to draw the analogy to alkenes. But by and large, what now we're going to do is I'm going to expose you guys to a lot of different reactions with carbonyls. Now, as we sort of pointed out earlier, right, we can often think about this, at least in terms of reactivity, as this sort of charged species, okay? Putting the positive charge on the carbon, the negative charge on the oxygen, and again, we'll sort of illustrate that here. Okay? And so a lot of the chemistry that we're going to do with carbonyls. So we've seen one that's catalyzed by acid, but a lot of times they're very, very reactive, and they can simply react with strong nucleophiles. Okay, and so some of the chemistry that you will sort of see is effectively analogous to other reactions that we've seen in the past with, say, for example, alkyl bromides, right? And so if you take a nucleophile, right, and you treat it with an alkyl bromide, right, what's going to happen? Br minus. Right, effectively what's happening is we're attacking where that delta plus is, right, moving the electrons over where that delta minus is, right? And drawing this sort of same analogy, sometimes for some of you, right, what might have been easier was instead of drawing it sort of SN2-like, maybe you wanted to draw it SN1-like, right? And perhaps what you wanted to do is draw this in a way where you had a carbocation, right, as the sort of first step, right, and then had your nucleophile attack, right, to get effectively the exact same compound. So with carbonyls, I think you can do it either one of these two ways, whatever's comfortable for you. You can either sort of draw it as the resonance form, first break that bond. What I will do primarily is I will treat carbonyls in the same way when I'm sort of attacking something with carbonyl. I'm going to push them all in a single step, sort of analogous to a sort of an SN2 process. So again, and we'll sort of see some of these, but the general idea here, right, is if you take a nucleophile and you treat it with a carbonyl, right, what's going to happen is you're going to get a new carbon-carbon bond, right? There will be a negative charge, right? If you've got a negatively charged nucleophile, we'll discuss some of these. What's going to happen is once you've attacked that carbonyl, you're going to end up with a negative charge on the oxygen. But in general, what happens at the end of any reaction that you run, right, is there's some type of workup. Generally, you take that reaction mixture and pour it on something like water, for example. And so the product that you get at the end of the day isn't necessarily the alkoxide that we've drawn here. It's not necessarily the negatively charged oxygen. What ends up happening is there's a workup. And what you will get to is alcohol, okay? And so when we're talking about chemistry of carbonyls, and specifically nucleophilic addition to carbonyls, what we're doing is we're generating a new sigma bond, right? And during this process, what we end up getting to is alcohol, right? So now there's some sort of complementary value that you may have here, specifically in synthesis problems, for example, to chemistry that you've done. Say, for example, with alcohol. All right, well, so what are some of the nucleophiles that we can use? All right. All right, so some of the really valuable nucleophiles you guys may have seen in the past, perhaps most recently, right, are alkynes. Right? Alkynes are nice nucleophiles in part because we can deprotonate them fairly readily, right? If you have a terminal alkyne, right? If you have that terminal alkyne, you can simply take it, treat it with a fairly strong base, sodium amide or something like that, right? You take this. Right? In this type of reaction, probably what you would do first is you would leave out the carbonyl first, right? Because you wouldn't want this necessarily reacting with the carbonyl. So you take these two, you mix them together, you deprotonate that, effectively generate the acetylide, right? And then that acetylide is going to react with this. And so what's going to happen here, right, is, well, I'll leave this guy out. I'll just go right to the acetylide. All right, but what's going to happen here, right, the acetylide is going to attack. Right, we're going to make a new carbon-carbon bond. This new carbon-carbon bond has an alkyne here. And again, during the workup, what's going to happen is you're going to get to the alcohol. So here's one example of a new reaction, right? You take this and treat it with a nucleophile. You get to this molecule here. Another reaction that's fairly common with carbonyls is the addition of cyano groups. So you can actually get away with just cyanide as well. Cyanide is its own little internal acid. So you may do a mechanism with just cyanide by itself, but certainly you can do, say, something like lithium cyanide or something like this. So if I took lithium cyanide, same thing's going to happen, right? You're going to attack. And following a workup, right, now we're going to make a new carbon-carbon bond, say, for example, so here's another reaction that we can do. But again, they're all basically the same reaction, right? You take a nucleophile, you treat it with a carbonyl, you generate an alcohol. These should all look the same. In principle, they're different reactions, but they're really the same. All right. Perhaps one of the most widely used carbonyl nucleophiles. Did you guys do Grignard?
Yeah.
Did you guys learn how to make Grignards?
Yeah.
Did you guys discuss Grignards in the carbonyl?
Yeah.
I'll just put it up there. Okay, so for those of you who weren't taking this course last semester, a really fantastic nucleophile that works really, really well with carbonyls is a reagent known as a Grignard reagent. You can make this fairly readily through alkyl halides. You guys have learned how you can make alkyl halides from alcohols, for example, or from additions of HBr across alkenes. You guys have learned a lot about working with alkyl halides. Traditionally, what you've seen with them is being electrophiles, but a Grignard reaction is a nice way to take them and convert them into nice nucleophiles. Okay? And there will be some analogies later on in the semester. What we're going to see is more organometallic chemistry, and so there'll be some parallels here between palladium catalyzed chemistry and magnesium, but effectively what happens in this reaction is that magnesium effectively donates a couple electrons into the R bromide bond. Don't worry about the mechanism behind this, but oftentimes magnesium is thought of as having a +2 charge on it, and so what we can think about this as being, the way that I often like to think about it is sort of an alkyl with a negative charge on it, at least for pushing mechanisms and so forth, and that the magnesium bromide has a net positive charge on it. So in terms of drawing mechanisms, right, I think it's oftentimes easier if you see it with those lone pairs free to react. It simply makes the mechanism easier, right? And so if you think about this more as a dissociated bond, it might just make the mechanism a little bit easier. Okay, and so once you have your Grignards will react phenomenally. So you make this solution, as you guys, many of you have already done in the Organic Chemistry 1 lab. And then what you're going to do is simply take this molecule, and you can take it along with a carbonyl source of some type. And what's going to happen is you're going to get the same mechanism I showed over there, following a workup, the alcohol. So again, Grignards are very versatile. You guys have learned how to make alkyl bromides. You can do the same with an alkyl fluoride or alkyl iodide. It doesn't really matter as long as you have some type of alkyl halide. You can make the Grignard from it. The Grignard can subsequently behave as a nucleophile to add into the carbonyls. Okay. All right. All right. So I think this is a good time to introduce another very mechanistically similar reaction, but for reasons that we will call something completely different, even though you will see it is the same reaction. This is a reduction reaction. Okay. Now, what if you're... So here we've seen a few nucleophiles. Now, what if you're What if your nucleophile was now, instead of being some type of an alkyl nucleophile, what if instead of it being carbon-based, right, was simply a hydride? Right? From the standpoint of a hydride, right, what's happening if the hydride adds in, it's no different. It shouldn't be any different. If we're making a hydrogen carbon bond, right? And then following the workup, right, what's going to happen to, let's say, water, the workup. What's going to happen is it's going to react with water, for example. And the net result is going to be the addition of hydrogen, H2, sort of across that double bond. Okay? So this is classically considered a reduction, right? And you guys have seen reductions in the past. And when you see the ability to add hydrogen across that double bond, in the same way that, say, for example, a metal is used to add hydrogen across an alkene or an alkyne to sort of reduce that bond, formally, right, a hydride-mediated reduction is also considered a reduction for that same reason. You are adding hydrogen across that bond. Even though from a mechanistic standpoint, right, it's much more similar to what we've seen previously in terms of substitution reactions, or in the case of the carbonyls, nucleophilic addition into carbonyls. Okay? Now the thing about adding hydrides into carbonyls is that something like sodium hydride generally isn't good enough, right? It's not, certainly have sodium hydride fires and stuff, so it's not to say that it's not a reactive reagent, but it doesn't really work that well at doing reductions. And so generally what we're going to see with reduction chemistry is a couple different reagents. But as this is a hydride, these reagents that we will discuss also have this hydride name to them. And there's going to be a few that we're going to discuss. We'll talk about a couple now, and I'll talk about one other later on. One of them is sodium borohydride. Right. Emphasis on the hydride. Okay. Sodium BH4. Okay. So it's effectively the borohydride, the boron with 4 hydrogens around it. Each of them have a very strong negative charge character to them. These happen to be very good at reducing. Now again, if you see a mechanism with sodium borohydride, I would just treat it as a hydride. Right? I think just for simplicity's sake, if you want to do a mechanism or you want to start thinking about how sodium borohydride works, just think about the hydride. That's the hydride. Okay? The other one that we'll see is lithium aluminum hydride. And what you're going to see is a very big parallel between lithium aluminum hydride structurally and sodium borohydride. Right? It's effectively, you'll go to the periodic table, lithium and sodium are on top of each other, or on aluminum are on top of one another. So structurally it's the same thing, but the aluminum, right, is now has the 4 hydrogens around it. Now, in terms of reactivity, if you guys, I'm just kind of curious as I'm sort of erasing this board here. As I'll sort of show you, the sort of choice of which one of these 2 reagents to use will be dependent upon what type of carbonyl you're trying to sort of reduce. And so in a moment I will get into nomenclature in a second. But if you start thinking about these structures, and I'll just maybe let you guys think of this for a second, and then I'll discuss nomenclature. But the borohydride, BH4, and the alhydride, ALH4. The question is, one of those is going to be more reactive than the other. And don't say it, but just think. Just think for the next few minutes as I discuss nomenclature. Aluminum is lower than boron. I'm kind of curious as to, or actually I'll just tell you. Aluminum hydride is more reactive, but I'm still going to ask you guys to try to come up with a reason why. All right, and I hate nomenclature. but I have to introduce nomenclature now, and it's important, right, because we discussed this. And so before we start talking about relative reactivity, now we actually, I can't really move on E4 further without discussing a little bit about nomenclature, okay? So carbonyls right, at their core are any molecule that has a C double bond to an oxygen. So anytime we're talking about a carbonyl, that's what we're talking about. Within carbonyls in general, though, there are multiple structures that we sort of discussed. We already discussed ketones. So a ketone is going to be any carbonyl where there are carbons on both sides of the carbonyl. So anytime you hear ketone, what we were referring to specifically is carbonyls with two carbons bonded together. Okay? We have aldehydes. Okay? Aldehydes are carbonyls where we have on one side a carbon and the other side a sort of hydrogen. We'll see there's big differences in terms of reactivity between these two. Okay? I'm not going to discuss carbon with a hydrogen on both sides, but does anybody know what that is? Because that's a molecule. It's not. That's formaldehyde, right? So that's not a type of carbonyl. That is a carbonyl. You can only have formaldehyde. You can't have types of formaldehyde. Well, I guess you can have paraformaldehyde, which is a polymeric form of formaldehyde. But anyways, I'm digressing. Aldehydes, ketones. What we will also have is molecules, and we'll see there'll be a couple differences here. You know what, I'll do this. Just to sort of save board space. So we're also going to have molecules where on one side it's a carbon, on the other side it's an oxygen. Okay. What we name them will be dependent upon what is over here. If R is a proton, right, that will be, does anybody know what that is? That's the carboxylic acid, right? So that's like acetic acid, right? These are acids, Bronsted acids. And if R is some type of a carbon source, then this would be an ester. Okay, so this is a carboxylic acid. Okay, in this case, it's an ester. And as we move forward, we'll start talking about other things. If you have a nitrogen where this oxygen is, that's an amide. Maybe we'll hold off on amides because I think we can sort of move forward discussing relative reactivity of these with just these. But there will be others, but for now, we'll just start with these ones. So know these names, be comfortable with those names. And in part, again, this is going to discuss, as we start talking about lithium aluminum hydride, we're going to begin, and sodium borohydride, there's going to be some big differences in how these react with these sort of different groups. Okay, now, aluminum hydride, more reactive. Anybody got any ideas? Yeah.
The boron is more about the fact that it's not going to separate from the sodium as much, and also aluminum is a metal, so it's more.
Well, boron's technically a metal too. No, but I like your idea though that about boron liking its octet more. It's kind of interesting. Yeah, it's interesting, and I got to be honest. I don't fully know the answer here. Yeah. So I think that relates to what was being more oxidation. You mean it can pull upon its d orbitals, which is maybe what was being said before. Yeah.
More electronegative, so more okay than negative charge.
Well, yeah, but the thing is that a negative charge, like, it's on top of each other, right? So as we start moving down the periodic table, yeah, it's very difficult to compare. So I'm sort of going back to stabilizations of anions, right? It's very difficult to compare vertically, but when you're comparing stabilization of negative charges across the periodic table, certainly electronegativity comes into play. When you're going vertically, even if it might not have the relative electronegativity when you're comparing top to bottom, bigger molecules will actually stabilize a negative charge better. So that's why something like That's why, for example, HI is a stronger acid than HCl, which is a stronger acid than HF. They stabilize the negative charge better, even though they're less electronegative. But good thought. Yeah.
Isn't that called polarizability?
So yeah, I mean, I think that's kind of hitting upon it in a way, is that at least what I would think, right, is when molecules are sort of closer to one another on the periodic table, the bonds are generally stronger, right? So something that like a carbon-nitrogen bond, right, is going to be stronger than, say, a carbon-phosphorus bond. And that simply has to do with the ability of the relative similar and energetic orbitals to sort of overlap well and have strong bonds. My guess would probably be that the aluminum-hydrogen bond is simply weaker than the boron-hydrogen bond, simply because aluminum has different p orbital. Yeah, I mean, it's a different layer, right? It's the three, you're talking about third level and first level compared to second level. So I would think it's the relative difference in the relative orbitals. But anyways, however you might be able to rationalize that, these are your big guns. Lithium aluminum hydride. I actually had a fire in my lab because of this stuff. My first semester here. It's kind of scary. It was an undergrad actually, and she was fantastic. She did exactly what she knew. She put the a glass what do you call them, the petri dish things or whatever, the watch glass right over the top, and the fire stopped. So very proud of her. All right. So anyway, so lithium aluminum hydride is stronger than sodium borohydride. So let's discuss the relative electrophilicity of these three compounds here. Okay. As we start thinking about the relative electrophilicity of these, which one's going to be the most electrophilic, right? Perhaps the best way to really think about this is based upon how well these molecules can stabilize the positive charge at this position. And I'm recognizing this might be a little bit, hopeful this will at least allow a trend that you can sort of think about, okay? Keep in mind, right, that in all of these cases, what we're dealing with here is a polarizable bond, right, where what we have at this carbon is a delta positive. The better the molecule is capable of stabilizing that positive charge, the less reactive it's going to be. Does that make sense? If that delta positive is less stable, then that molecule will be more reactive. It's going to want to help that positive charge, if you will. Okay? So if we start thinking about the relative resonance forms and think about the stabilizing of that positive charge, it's probably easier to see the relative stabilization by looking at it in that resonance form. And we were to rank these which one of these resonance forms might you think, or which one of these carbocations do you think is the most stabilized? Yeah. So I've got one vote for the top right. Now let's think about the differences here, right? They're all the same except for those things that are circled. Okay, so I've got one vote for the top right. Why? So you're drawing upon hyperconjugative stabilization. Okay. Yeah?
Bottom right?
Well, there's only a bottom. Yeah. Why?
Maybe the resonance structures of the two different options.
Okay. Okay, what? Okay, no, but you were thinking right. No, but I like that because, but this is it. This explains everything here. But this explains everything here, right? You're saying hyperconjugation is good. Well, guess what's better than hyperconjugation? Full-blown resonance stabilization. This is conjugation. This is hyper, kind of semi-conjugation. This is full-blown conjugation. So you're stabilizing with the ester through straight-up conjugation, right? So this is the most stable. This is the middle, right? And then this is going to be the most, or I should say, the least stable. Okay? So again, we could also make other arguments about aldehydes, right? They are perhaps the most accessible sterically as well. That's one of the things you can think about as aldehydes, right? There's nothing else there, it's just a little proton, so there's not going to be anything to get in the way. But you can at least reason this entire situation based upon electronics. And I think that practicing and getting comfortable thinking about electronic properties of different things is often a way to go, okay? So, as it turns out, trying to put up something here that's going to be sort of make sense, right? But most reactive is carbonyl, is the aldehyde, ketone, and we'll get back to carboxylic acids in a moment. But as it turns out, lithium aluminum hydride, again, is the big guns. It will reduce all of these. Okay, so if you took any single one of these, they will all react. They will all react with lithium aluminum hydride. They will react violently, quickly. Well, the esters might be a little bit more sluggish, but they will all react very quickly. We'll get back to in a moment what esters actually go to. And in the case of sodium borohydride, aldehydes work great, right? Aldehydes you can reduce really quickly. You can also get ketones to react with sodium borohydride. Now here's the thing with ketones, is that sometimes the ketones can be a little bit more sluggish. So on occasion you might actually be able to get an aldehyde, say for example, to reduce without actually touching the ketone. So the ketone is less reactive, and you can get it to go though. So sodium borohydride will react with ketones, but they're going to be faster with an aldehyde. Okay? Esters are very, very, very hard to get to go with sodium borohydride. I've seen examples of people being able to reduce esters with sodium borohydride, but generally you have to like reflux, really high temperatures, and so generally you're not going to reduce an ester with them. So for the sake of this course, we will say that yes, yes, and no over there. So for the sake of us, we'll just say esters will not reduce. They can, but again, it's much more forcing additions, okay? And so you have a little bit of flexibility here, right? If you have a molecule, say, for example, that has an ester on it and has a ketone or an aldehyde, you could reduce that ketone or aldehyde in the presence of the ester, so you have a little bit of sort of flexibility here. Okay, so we've only got about a minute left. And so what we're going to talk about next week, in our first class next week, and what I want you guys to all understand and know why, is when you take lithium aluminum hydride and you react it with an ester, it goes down to the primary alcohol, okay? So that's what I'm going to leave you guys with. So we'll discuss this at the beginning of the next class. But come up with a reason why you can't go from an ester to, let's say, an aldehyde, right? It's going to go all the way to the alcohol, yeah.